to explore and respond to the Nolian request with in the context of calibration. So I'd like to go to help, and I'd like to go to example models in help. It's the time that we've sought recourse in the course of since the Schelling segregation. So I'd like to scroll down here, and we're going to look to SIR agent-based calibration. Let's do that again. So I did help, example models. Okay, I don't know why it's there we go. And then scroll down here and go to SIR agent-based calibration. Boom. So now this is loading a new model. And what we'll see is, although this model is new, and although it depicts a situation with different than the one we talked about in terms of its details, there's much commonality. And I want to draw attention to this calibration. You notice it contains and a calibration experiment, okay? Now, this calibration experiment has some nice displays of things, and we'll talk about those a bit over the lunch. But the main thing I want to draw your attention to, the thing that bothers people, the thing that's opaque to people, the thing that people find it hard to pierce logically, the thing that they find it hard to overcome, lies before you. It lies before you. And it's nothing. So basically what's going on here is that we have, for calibration, we are trying to match up model results against empirical data. Data that typically cannot by itself be reduced to particular parameter values. So there's a lot of data out there in the world that is data from a system that exhibits causal tangling of many factors. We can't tease out just a parameter for our demographics of our model, or just a parameter regarding the transmission of norms, or just a parameter involving the likelihood of behavior change. Rather, it reflects all of those. And typically, most data that we deal with empirically is of this sort. It doesn't neatly allow us to deduce this parameter or that one. There's a lot that does, but there's a lot that's at a high enough level, it's tangled. It's entangled. Now, we want to make use of that data in our model. And so one of the ways in which we do that very commonly is we try to match our model to that data, to build confidence in a model, but further, to try to identify for those model parameters where we don't have good bounding, good empirical data, perhaps latent variables, what have you, we try to adjust those to best match the data that is available. So perhaps there's some aspects of the situation that are little known, where we don't have recourse to good data sets. And we'll adjust those parameters to best match historic data. So this is a model. This is a model where we have in it, if you go look at calibration, within here, there's this data set infectious historic here, okay? And this is based on a table function, something that says for this time, use this value. And you can go into the preview area. This is our historic data, ladies and gentlemen. This is the data that we want the model to try to match in its results. To try to match this data up in terms of the number of people who are infected at a given point in time, the prevalent case counts of infection over time. So there's this data, infectious historic. And you'll notice there are these data sets here. Okay? Including something called DS infectious historic. Let's go now look at how this parameter experiment works, this calibration experiment works. And we'll see that it has many features of what we've been seeing in the parameter variation thing. Does anyone recognize this line? What is that doing? Just resetting the data that it would otherwise get accumulated, right? Does anyone recognize this line, after simulation run? What is that doing? You know the sound associated with it. It's sucking out this data set. We've done that before, right? From main, and it's populating it into some data set here. Now, we did it into a data histogram 2D, but here it's doing it into a local data set. And that's fine. So here, once again, it's salvaging information from main regarding the number of people over time, the prevalent case count over time, just like we did, and it's storing it locally, okay? And those are key components. Now, there's an additional piece to this, though, that wasn't there in the parameter variation experiment. These basically mirror what we did, right? We reset and we sucked out the thing every time from main. Sucked it out and we stored it locally. Great. We stored it in the experiment. Excellent. Okay, so wherein are some of the differences? Like this thing, what's this all about and so on? Well, let's go up and look, because there's a key piece that's different. Here, ladies and gentlemen, far from just running the model many times with the same parameters, what's going on is it's actually adjusting parameters. Which parameters does it adjust? It adjusts those here in this parameters area. It's adjusting two, contact rate and infection probability, which personally I think is a bad choice of two parameters. But really it should do contact rate and average duration is a nicer example. Anyway, so here, what we see for the objective, well, we see an objective. It's adjusting these parameters, just like that, between these ranges. And it's trying to minimize, trying to get as good a match as possible, minimize the discrepancy, minimize, in short, the difference between the two. Between what? The difference between the historic, and guess where this comes from? From the capital M, ends with L, has a D in the middle. From the model. Thank you. Yeah. As in the Greek chorus. So here, this is specifying some rule, taking a way to quantify a discrepancy between, on the one hand, the historic data and what the model produces. This is a function that AnyLogic provides difference here. Okay, this basically computes, computes some square root of some squared differences. It's actually this one we're using here, the second one. Boom. Difference function always non-negative, reflects difference between data sets and the common arguments range. But if you scroll down, it returns a value, returns a number. And we're trying to minimize that number by adjusting these parameters. What does this number represent? It's the square root, the average of the square of differences between linearly interpolated data sets. So if we have these two data sets, one historic, time 0, it says this many. Time 1, it says this many. Time 2, it says that many. And then, now we have data from the model. Time 0, it says this many. Time 1, it says this many. Time 2, it says this many. It's comparing each of those in turn, taking, for time 0, takes the square of the difference between the historic and the model-generated one. Time 1, it takes the difference, square of the difference between those two. And it is taking the average over all the time and then taking the square root of that. And so in short, it's computing a degree of discrepancy. How far different are the model's guesses from the historic ones, the historic data? And then being able to do that for a given model run, a given run of main, it's adjusting these parameters to minimize it. So it's saying, oh, gosh, that's a big discrepancy. I was better back there. And so it adjusts these parameters to try to explore the space. Oh, it's getting really bad here. oh, wow, this is looking pretty good. Oh, this is much, much better. And it's adjusting these parameters to try to get it as close as possible. Now, while all this is going on, this is functionally what's happening. At a high level, this is what's going on. It's exploring different values of the parameters in clever ways in this kind of two-dimensional space. One parameter, the other parameter, kind of exploring, where is it good, where is it not so good, evaluating this for every run. Every time I adjust a parameter, I have to run the model, right? Run the model, say, okay, how many people are going to be infected this time, that time? It's going to run the model. Every time it tries a new parameter, it's going to run the model, and guess what it has to do after it runs the model? That's exactly what we were seeing. It has to suck out that data from that model as to how many people are infected over time, put it in a local thing, and then apply that difference function we just saw. So okay, I want to look at it for contact rate of this and average illustration of this, or infection probability. Fine, I'll just go with what they have. Average infection probability of this. It runs the model, and then it sucks out this data. It sucks it out into this DS infectious current, and that lives in experiment because we don't want it to go away suddenly. It was in main, but main's going to die. Main's going to be reused again and again and again. It's going to die. It's going to be destroyed and brought back and a new one is going to be created. Destroyed back. So we suck out the data from it to somewhere we can store it. That's DS infectious current. We brought it into us. Okay, we got this data. We sucked it out of main and we salvaged it. And we're comparing this to historic, seeing how big the difference is and how big the difference is in adjusting further. Now, if you had several data sets you wanted to compare, maybe you have data sets related to incidence and prevalence. Maybe you have data sets related to the number of deaths and the current prevalent case count. You would add them together here. Difference in this one, difference in this one, difference in this one. And I have a nice exercise students of mine do where I give them several data sets and I say, go calibrate it and learn from it. And they say it's a good exercise to go through. That's when they really understand what's going on here. Okay, so that's the kind of the basics of this. We can either maximize this or minimize it. In this case, we're minimizing it because it's a discrepancy. And then there's some other stuff going on that's less essential, less central. So basically, and this gets this issue of iteration, simulations, and experiments. So the experiment is the whole thing. You're going to run this whole darn thing to do this experiment to adjust these parameters. It's going to run main again and again and again and again. Okay, fair enough. So you're going to run this whole thing and get out some good results out of the end. Some best parameter values for which it matched the best. Great. But guess what, folks? Oh, man. We have this uncomfortable reality. The uncomfortable reality is for a given simulation run, we can suck this out. But from simulation run to simulation run with the same parameter values, we may get variability, right? Remember we saw that. We just saw that in that thing we ran with the parameter variation experiment. It's one of the virtues of doing that first. We saw that a given run of the model with a given set of parameters, not varying any parameters, there's variability, isn't there? Sometimes it's higher, sometimes it's lower at a given time. So if we're doing this calibration, we're trying to match the simulation model against the empirical data in the most reliable way. We don't want to just run the simulation model once for a given parameter value. You may get a fluke. You may have a really great match, but that was just that chance for that time. Or by conversely, maybe it was a really bad match just for that time. So what do we need to do? Well, we delineate a single run of the model, a so-called simulation run. And unfortunately, the terminology here is a little bit regrettable, confusing. From iteration. Iteration means an entire try of a given set of parameter values, a given assumption about the parameters. Maybe it's infection probability equals 0.37 and contact rate equals 22.6. That's one assumption. And the thing is, folks, that we may run the model multiple times for that, and generally we do. So in calibration, with a stochastic model like we have here, or like is used for this example, we're going to be running it again and again and again with the same set of parameter values. And that, somewhat confusingly, is known as running multiple replications. I prefer the term realizations. But these replications mean that we don't just trust it to run it once for a given parameter assumption. A given assumption about the parameters. You know, contact rate equals 22.5 and infection probability equals 0.37. For that given assumption, we'll run it not once, but here 5 times, this replications. Now, what happens behind the scenes here, and you can get it, you can spy on it in a certain way, and I think in my little problem set, I suggest ways of doing this. But basically, it takes the average over the discrepancies for these to judge which is best. So you could run it 50 times if you wanted to, and it would take the average of the discrepancy over the 50 to figure out what's best. So if we look here, within the discrepancy here, you see it says if current iteration is best iteration. This is something it's kind of filling out, which is the best based on the average discrepancy for each of the simulations, each of the particular runs, each of the realizations, each of the replications. It's doing this, sucks it in, does the difference up there that we talked about, and then for each one of those, for a given assumption about parameter values, it's totaling them up and taking their average, and figuring out, is that the best we've seen thus far? If so, after, and this is the key thing, after the iteration, this iteration is after we're done with all of those replications for a given parameter assumption, then we can say, hey, is this the best one thus far? If so, take this latest run, this is an uncomfortable fact, just the latest one that it's paying attention to in their default code here, and pull it into our kind of best run result. The thing that's a little bit funny about this is just the latest latest of the 50 runs, latest of 50 replicates. There's nothing terribly privileged about this, not even the average of them. That's just their code. You can replace it with yours where it's the average or whatever, but the point is that it sucks that one into the infectious best just so it can display it. It's nothing terribly deep about it. It just wants to display it. So if you run this thing, watch this. And I have lectures on this online where I think I go into this for 2 lectures in a row or what have you. There you go. So what's going on here is here's some empirical data in yellow, and you'll notice that it's trying for different replications, different particular runs of the model, and it's showing that blue. And this best is the set of parameter values for which it's best. It's showing the final run for that. So you hear us a run that was not terribly good, but this is, you notice that this is kind of keeping track of how the discrepancy is thus far, and its best run thus far. Its best set of parameter values, how good is it? And you can see it started out pretty bad math, coming down and down. And so it's getting closer and closer to this kind of underlying historic data. It's matching up that underlying historic data with model results. And there's a little bit of funny business going on here because it's actually using something called OptQuest behind the scenes to kind of do the optimization. And to actually get it to display things here, like these values, you actually need to say, give me the OptQuest variable called such and such. It will tell it to you. Give me the best value in OptQuest. And so there's a bit of funny business there that if there's real interest, I can talk about and show you how it works. But I've tried to give you the gist right now. The gist of it basically should be pretty darn familiar from the parameter variation experiment, because you have basically the same reset, suck it out of the main, and then accompanying that by sort of the unique feature, which is this discrepancy function up here, and you're doing that as it's varying these parameters, and you may be using replications to run it many times and it's taking the average of them in order to judge it's the best iteration, where iteration means this collective set of replications for the same parameter value assumptions. Does that make sense? Okay, I'm happy to go into this, like, nerd more about it by showing you the OpQuest stuff, because it's a bit funky, but it's actually not that bad. Yeah? Yeah. Right. Right. Well, okay. There's a deep issue here. Is the lunch out there? Okay. So maybe we should talk about this, because I feel bad holding people for lunch. It's a deep issue. So when I'm talking about this, I'm talking about the mechanics and some of the plumbing. The truth is that that calibration is a bit of an art, like doing calibration well. It happens to be an art that my group has quite a lot of experience in, and I myself have spent many, many hours nursing along calibrations and learning how to overcome barriers with them. Because you get into these barriers where it's in a local minimum and thinks it's, this is the best, and you're suspicious there may be something more, and there's ways you can get it to kind of deal with that. There's also ways to deal with high dimensional spaces where you have large number of parameters that are uncertain. There's different strategies different folks take to kind of deal with that situation. Generally speaking, the more parameters that you have loosey-goosey, the more parameters that you have that need to be pinned down, you want more empirical data to ground them. Otherwise, there's identifiability issues. There may be many possible assumptions about the parameters that match quite well the limited amount of empirical data. And so there come in some real identifiability issues. And we've developed tools that we've used a fair bit in the past to give insight as to sort of what's going on, why is it ambiguous about the interpretation of this. It turns out there's also some types of data that you don't want to try to just match in a point-wise fashion. I mean, it's all well and good to talk about matching a nice outbreak curve or something like that, but there's some data, and you can do it even in the presence of noise. We've done quite a lot of this. But there's some types of data where really the thing you want to match is not point-by-point matches. It's instead the qualitative features of it. And the system dynamics field, I think, to its credit, has had some thoughtful kind of thinking about this, thoughtful reflection on this issue. Try to capture oscillations, for example. And physicists and those in the ABM community have also talked about capturing the patterns without trying to capture all the vagaries of exactly, the numbers. I mean, you think about think about looking down from a bridge into water, right? You may have a wonderful model of how water flows, a wonderful computational fluid dynamics model that captures how water behaves. It's, tremendously powerful model, but it will be a fool's errand. It will be just crazy to try to say, well, we're going to judge this model, have to point predict every wave and the height of every wave there. I mean, as I say, it's a fool's errand because the model may be very good, but our ability to sort of pin down everything in the world that shapes that wave and its history is kind of ludicrous. Instead, what we try to do is we look to kind of the model matching at a phenomenological level what's going on in terms of the frequency of the waves and their height and their viscosity or whatever it is. So we have these physical measures that are more order parameters that sort of capture for us the nature of the system at an aggregate level, and we try to match the model against that. It may not be an aggregate model, but it's a model that we use to judge against that rather than on a point level. And so that gets to be a little bit of an interesting issue. When do you try to point match, and when do you just try to capture the trend, capture the oscillations or the mode of behavior? When do you try to capture the sort of the nature of the sort of variability within the data set in terms of the range of noise, for example. These are things that go to point prediction, and personally, I think they're pretty important. And this whole notion of pattern-oriented modeling and ABM, and there's a similar, there's a notion in system dynamics about matching qualitatively and these statistics, field statistics, that are used to sort of capture features of the situation while trying to abstract away from the exact numbers. And that's also a big issue. But we can talk, if there's interest, a little bit more after lunch, bearing in mind that we'll want to push forward soon.
Yeah, or maybe you could just direct us to your latest calibration online.
Sure. Yeah, I mean, I go into a lot more detail, but what I can't impart well online is the art of it. And I do have slides, which I've created before, giving very practical advice. Okay, you have a calibration exercise. These are the things you recommend you do if you get stuck, if it seems to not be matching well, but it can't figure out a better one, this is what you should do. Suppose you have lots of parameters, what are some advice for dealing with it? I know certain groups do, they call it unpeeling the onion, so you do the most core parameters first, you fix those, and then you do the next outer set and the next outer set. That's one way of trying to deal with it. The point is there's some kind of practical skills and advice that comes up in this area that I'd be glad to share, but we don't have time to talk about it here. Yep. Okay. So I think it's time for lunch. Great.